Okay, today I'll be talking about a question I did. To be honest, though, this question I still don't fully understand it, so bear with me as I just explain what I learned from it. So this question, I've been afraid to do it for so many days because I just don't know what's going on in the problem. We suppose that the number of children that a family has in the US is n follows a Poisson distribution with parameter lambda. We prescribe a prior distribution of lambda follows gamma distribution, where we use the Sharpe rate parameterization. We then observe 34 families who have a total of 100 kids combined. Find the posterior mean for lambda. So like basically in this question, we have something called Bayesian updating problem. So we start off with the likelihood, which is our n follows the Poisson distribution. So it's just kind of like what we think um, the lambda represents in here the true average number of kids per family. So we don't know what that is. So we're trying to figure that out. So that's what it says. And then the prior is what we assume is it follows this gamma distribution over here with parameter 32 and rate parameter 10. And then we had collected data, which we surveyed 34 families, had 100 kids in total, and we're trying to find the posterior mean, which is just our updated guess based on the new observations we have. So before, if we're doing a lot of like combining distribution, it's kind of like pretty difficult. But inside here, there's this new concept I learned called conjugate priors. The idea is that because we have gamma and Poisson, which is kind of both the rates, and they combine nicely together, so which are called conjugates, they mix up to produce another gamma distribution. Um, so basically what we can do is we can update the shape. The shape is just the old shape plus the total kids observed. So there were previously 32. Now we added 100 to the sample, so we have 132. And then the rate is just basically we have a old rate and then the total families observed. So we have 10 plus 34 is 44. So our updated belief, which is our posterior distribution, is gamma of this. And then our final thing of how we find it is we're asked for a posterior mean. Posterior mean using the gamma distribution of the shape rate parameterization. It's just the Sharpe divided by the rate. The Sharpe over here is the 132, and then the rate is 44. So our mean is 3. So that's why our posterior mean is 3. Some things that I further followed up was over here we have um talking about the reason of why the shortcut works. So it really comes down to like this conjugate priors, right? We have this Bayes' theorem, like the one that we're familiar with, is that the posterior is proportional to the likelihood times the prior. And then the likelihood is just following the Poisson distribution, which is like this, right? Um, and then our prior, which we assumed for the gamma distribution, looks like this. And if we combine this together, this posterior is proportional to this thing over here. So then we have this form, which is again of the form of a gamma distribution, right? So our thing is this new shape is this alpha plus s and then beta plus n. So that's how we get exactly the thing over here. And then I was first confused about rate. What it means by rate is actually just the per of the parameter b is just what is it called? Just what it means is that rate is just kids divided by family. So it's not actually a rate. And then the units of prior like is calculated by Sharpe divided by rate. So that's just alpha divided by B. So it's kind of like just a lot of vocab that I was not familiar with. And I guess this is just the first introduction of this. I think I'll learn a bit more and then do the question. Okay, that's it for today.